Imagine this. You're strapped into a sleek spaceship, hurtling through the void of space at a fraction of the speed of light. Stars blur into streaks, and in just a few days, you're sipping coffee on Mars, watching Earth as a tiny blue dot. Sounds like science fiction, right? But what if I told you the key to making this real is something straight out of a Hollywood blockbuster? Antimatter, the stuff that could blow up the Vatican in Angels and Demons, or power the Enterprise in Star Trek. Yeah, that antimatter. Welcome to today's video, where we're diving deep into why antimatter is hailed as the ultimate fuel for interstellar travel. If you're a space nerd like me, buckle up. This is going to be epic. Hit that like button if you're excited, and subscribe for more mind-blowing science breakdowns. Let's blast off. First off, let's get the basics straight. Antimatter isn't some made-up villain from a comic book. It's real physics. Remember Einstein's famous equation, E equals mc squared? That's the secret sauce. When antimatter touches regular matter, like the stuff you're made of, they annihilate each other, turning 100% of their mass into pure energy. Compare that to your car engine, which squeezes out maybe 0.0001% efficiency from gasoline. Antimatter? It's 10 orders of magnitude better. That's a 1 followed by 10 zeros more powerful. 1 gram could unleash energy equivalent to about 43 kilotons of TNT, enough to level a city. Scary? Absolutely. But harnessed right, it's the ticket to the stars. Think about it in movie terms. In Star Trek: The Next Generation, the Enterprise uses a warp core powered by antimatter reactions to bend space-time and zip across galaxies. It's not just fantasy. Real scientists at NASA have drawn inspiration from that. Or take Angels and Demons. Tom Hanks races to stop a tiny vial of antimatter from exploding in Rome. That scene where they created at CERN, it's based on actual tech. CERN, the European Particle Accelerator Lab, really does produce antimatter particles, though in minuscule amounts. In real life, back in 2010, they trapped 38 antihydrogen atoms for a fraction of a second. A breakthrough that had physicists cheering like they just won the Super Bowl. Now, let's talk potential. Why is this stuff the holy grail for space travel? Energy density, folks. Current chemical rockets, like the ones in SpaceX's Starship, are great for getting to orbit. But for deep space, they're like trying to cross the ocean in a rowboat. Antimatter could propel ships to 10 to 40% the speed of light. That means a trip to Mars, which takes 6 to 9 months now, could shrink to days. Imagine colonists waving goodbye on Monday and unpacking on the red planet by Friday. For interstellar jaunts, Alpha Centauri, our nearest star system at 4.3 light-years, would take 10 to 40 years instead of thousands with today's tech. That's within a human lifetime. Real-life example. NASA's New Horizons probe took 9.5 years to reach Pluto in 2015. Snap in those stunning photos of icy mountains. With antimatter, you'd get there in 3 to 4 weeks. Think about the implications. Scientists could send probes, get data back quickly, and iterate on missions faster than ever. Or picture astronauts on a manned mission to Jupiter's moons, exploring Europa's potential ocean life without aging a decade en route. It's game-changing for exploration. But how would an antimatter engine even work? Picture this. You store antimatter in magnetic bottles. Think penning traps, like invisible force fields, to keep it from touching anything. Then, you mix tiny amounts with matter in a reaction chamber. Boom! Annihilation releases gamma rays and particles, which you channel into thrust. Concepts like antimatter-catalyzed fusion use even smaller amounts to kickstart nuclear reactions, making it more feasible. In TV shows like The Expanse, ships use efficient fusion drives for realistic space travel. Antimatter could supercharge that, turning sci-fi into sci-fact. Of course, Hollywood loves the drama, but real challenges are even wilder. Production is the big bad wolf here. Antimatter doesn't exist naturally in bulk. We have to make it in particle accelerators. At CERN, they're churning out antiprotons at a rate of about 1 to 10 nanograms per year. To get 1 gram, it'd take hundreds of millions to billions of years at current speeds. That's longer than the universe has existed. A 2025 breakthrough using laser-cooled ions boosted production 8-fold, but we're still talking femtograms, trillionths of a gram. Cost? Buckle up. Around $62.5 trillion per gram. That's more than the GDP of most countries. Why so pricey? It takes insane energy to smash particles together in colliders. Efficiency is abysmal. Less than 0.0000001% of input energy becomes antimatter. Real-life parallel. Remember the Manhattan Project? Building the atomic bomb cost billions in today's dollars and pushed tech limits. Antimatter production would need a similar moonshot effort, maybe dedicated factories in space where solar power is free. Storage is another nightmare. Antimatter annihilates on contact with matter, so you need perfect vacuum traps with superconducting magnets. One glitch and kaboom! Gamma rays everywhere. In Interstellar, Matthew McConaughey's ship deals with black hole radiation. Antimatter engines would require heavy shielding against their own exhaust, adding tons of mass. Safety risks? Huge. A gram's worth could mimic a nuke, so imagine launching that from Earth. One accident, and it's goodbye, Kennedy Space Center. Let's sprinkle in some real-world grit. Back in 1999, NASA funded the propulsion antimatter concept, exploring beam core engines where antimatter protons annihilate to produce charged particles for thrust. It was promising, but shelved due to costs. Today, private players like Positron Dynamics are tinkering with positron-based propulsion. Positrons are antimatter electrons, easier to handle. They're aiming for satellite thrusters first, a baby step toward bigger dreams. Future outlook? It's not all doom and gloom. Near term, we might see hybrids. Use micrograms of antimatter to trigger fusion, slashing fuel needs. NASA's AIM-STAR concept from the 90s proposed this for outer solar system probes, cutting Pluto trips to months. By 2030 to 2050, if we boost production 100 times, we could test small engines. Military interest, think DoD studies, could speed things up, but ethicists worry about weaponization. Remember the Cold War space race? Antimatter could spark a new one, with China or the EU joining in. Hollywood often glosses over the grind, but take The Martian. Mark Watney survives on potatoes and ingenuity with chemical rockets. Antimatter would make his rescue a breeze, but it highlights how far we are. Or Ad Astra, where Brad Pitt's journey to Neptune takes months. Antimatter could turn that into weeks, exploring psychological tolls in a new light. Wrapping this up, antimatter isn't just hype, it's physics' promise for humanity's next leap. Useful tip: if you're inspired, check out CERN's Open Data Portal or NASA's propulsion papers online. They're free and fascinating. For students, major in particle physics or aerospace. This field's exploding, pun intended. And hey, support space agencies. Public funding drives breakthroughs. If we crack this, interstellar travel becomes real. What do you think? Will we see antimatter ships in our lifetime? Drop your thoughts in the comments, share this video, and let's geek out together. Thanks for watching. See you in the next one. Peace out.